Hey, what's up everybody? It's Mr. Boylan. Today we're going to continue talking about how chemical equilibrium can be used to describe the proton transfer reactions of acid-base chemistry. Now, specifically today, we're going to take a look at the salts of a neutralization reaction between an acid and base is acidic or basic, and then we're going to calculate the pH of those salt solutions. So first, any salt can be written as the product of a neutralization reaction of an acid or a base. As you look at your screen there, you've got your general formula for your acid, your general formula for your base, forming water, and your salt. Again, just generalized formula here. The M is the cation coming from your base, the A is the anion coming from your acid. Now, one of the big things we're going to talk about in this video is to determine whether or not the salt of that neutralization reaction is acidic or basic. And how the salt will affect pH comes down to whether or not the ions of that salt will hydrolyze or split water to any significant extent. And so as you look at the general equation that we have there for a neutralization reaction, I have taken my generalized formula for a salt and split it out into a cation and anion. We're going to take a look at the cation first. Recognize that this is a reaction that's happening in solution. There's lots of water around. And the question then is, will this cation hydrolyze or split water? And as you observe the hydrolysis of water by that cation, it produces additional hydrogen ions in solution. And so if this happens, then we say that salt is acidic. Let's take a quick look now at the anion of that same salt. If it is able to hydrolyze water, it will form additional hydroxide ion in solution, therefore indicating that it is a basic salt that was formed in that original neutralization reaction. Now, let's take a look at three different situations that you'll be presented with on the AP test. The first is going to be the neutralization of a strong acid and a strong base. In this example, we're going to get a neutral salt. Let's talk about why. The example that we're using here is hydrochloric acid and sodium hydroxide, both examples of a strong acid and a strong base, respectively. How would you know that? Well, this is where it's going to be really important that you memorize your strong acids and your strong bases. Now, let's take a look at the ions of this salt. First, the cation. The sodium ion, will it hydrolyze? Will it split water to form hydrogen ions? Is this going to happen? No. Why not? Because sodium hydroxide, what you saw formed there momentarily, is a strong base. And that's going to stay completely dissociated, completely ionized in solution. And so this reaction is not going to happen. Similarly, if we take a look at the anion in sodium chloride, we wonder, will this react with water? Will this hydrolyze or split the water molecule to create additional hydroxide ions? No. Again, if it were to happen, it would create HCl, which is a really strong acid, which is not going to stay in its molecular form in solution. It's going to stay ionized in solution. And so neither of these reactions will happen. We will not see either of these ions hydrolyze water. And so our salt, sodium chloride, is considered a neutral salt. Now, this is what you're probably most familiar with as you think back to your first year chemistry class, where we really just did strong acid and strong base titrations or neutralizations, where we made a neutral salt. No additional hydrolysis of water, no additional H ions or hydroxide ions, so you're going to have a pH of 7. Now, let's take a look at the neutralization of a strong acid and a weak base. In this example, we're going to get an acidic salt, and let's talk about why. Here we've got hydrochloric acid, which is a strong acid. Again, you're going to have to memorize that. And iron 2 hydroxide. This is a weak base. I can recognize that because iron is not one of my group 1 or group 2 metals. But let's take a look now and see what happens with these ions of the salt that's produced. The cation will react and split water molecules. We are going to get the formation of this iron 2 hydroxide. Because this is not completely ionized in solution, we will get some splitting of the water molecules to form some additional hydrogen ions. The chloride ion, however, is not going to hydrolyze or split the water because HCl is a strong acid, and so it's going to stay as its ions in solution. So if we have the iron ions from this salt hydrolyzing water to produce additional hydrogen ions, we say that this is an acidic salt. And your pH of your solution is going to be in the acidic range. So a strong acid and a weak base will produce an acidic salt. The cation of that salt will hydrolyze or split water. Additional hydrogen ions will be formed, an acidic salt. And then lastly, we've got a weak acid and a strong base. This will give us a basic salt. Again, as you take a look at that generalized equation for a neutralization reaction, we're going to put in specifically hydrosulfuric acid and potassium hydroxide. Again, a weak acid, it's not one of our 6 strong acids we were asked to memorize. And then this is a strong base. We've got group 1 metal hydroxide here. So a strong base, a weak acid. We're going to take a look at the salt potassium sulfide. Is this going to be an acidic or a basic salt, and why? Let's take a look at the cation. Will potassium hydrolyze or split water? Well, is this going to happen? No, we're not going to have potassium hydroxide form. It's a strong base. It's going to stay as its individual ion. So that reaction is not going to happen. As we look at the anion in this case, we will see the formation of additional hydroxide ions when the sulfide ion hydrolyzes or splits that water molecule. H2S does not completely ionize. It's not a strong acid. And so we will see this reaction happen. Therefore, additional hydroxide ions will be produced. Therefore, this salt will be considered a basic salt. So a weak acid and a strong base produce a basic salt. The anion of the salt hydrolyzes water. Additional hydroxide ions are formed. Now, you might be asking yourself, oh man, I'm so confused. Is there an easy way to tell? Yes, strong always wins. So if we come back to those 3 examples that we just worked through, the first example was a strong acid and a strong base. Well, since they're both strong, we don't have a winner, if you will. Therefore, we produce a neutral salt. In the second example, we had a strong acid and a weak base. So the strong acid wins, which means we get an acidic salt. And finally, we had our weak acid and a strong base. The strong base is going to win out here and produce a basic salt. So that's probably the easiest way to tell what type of salt is going to be forming. Go back to the parent acid and parent base to determine which of them was stronger, and that'll tell you how the salt is going to behave. Okay, so when you are going to solve for the pH of a salt solution, you need to recognize the relationship between the ionization constant Ka of a weak acid and the dissociation constant Kb of its conjugate base. Now, in your notes, it works through how the relationship is derived. This formula is given to you on your formula chart. It's not something you have to memorize, but it's an important relationship that you recognize when you're working through solving these calculations for pH. This means basically that if we know or we're given one of these values in the problem, because Kw is a constant, we can always figure or calculate the other one. Now, as we'll learn, this is important because once you are able to determine either Ka or Kb, you can use either of these relationships, which we can derive from an ICE table, which we'll practice, to determine what the hydrogen ion or hydroxide ion concentrations are. And then if you know those concentrations, you can just plug them into the formulas for pH or pOH, which are just the negative logs of those respective concentrations. Boom, you've solved for pH or pOH.